Somewhere on Earth right now, people are building infrastructure in places where a human can die in hours without protection, where machines fail faster than they can be repaired, and where nature actively tries to shut every project down. These are not experiments. They are critical systems. And failure is not an option. For most people, construction is associated with cranes, concrete, and predictable urban environments, yet some of the most important infrastructure on the planet is being built in locations where survival itself is uncertain, where heat, cold, altitude, and isolation impose limits that no spreadsheet can fully capture. These are the world's most extreme construction zones, environments defined not by convenience or efficiency, but by conditions that actively resist human presence, forcing engineers to rethink what it means to build at all. In these places, engineering is not simply about structures or materials, it is about sustaining human life, machinery, and logistics long enough for construction to even begin. Across deserts, polar regions, and high mountain ranges, modern civilization is pushing infrastructure into zones once considered inaccessible, not because it is easy or impressive, but because strategic necessity leaves no alternative. Energy security, logistics corridors, climate monitoring, resource access, and geopolitical positioning increasingly depend on infrastructure that must exist far beyond comfortable environments. This marks a new phase of industrial development, where survival engineering becomes as important as structural engineering, and where failure carries consequences that extend far beyond delayed schedules or budget overruns. In extreme deserts, the challenge is not simply heat, but the absence of everything else. Temperatures reach levels that degrade both the human body and sensitive electronics, while sand infiltrates engines, joints, and sensors with relentless efficiency. Construction zones in regions such as Western China, the Middle East, and parts of North Africa are shaped by dehydration risk, thermal stress, and supply chains that stretch across hundreds of kilometers of barren terrain. Water logistics often become the single most critical constraint, forcing planners to treat hydration, cooling, and medical readiness as core engineering systems rather than secondary support. Workers rotate in short, controlled shifts, equipment is modified with reinforced filtration and cooling systems, and automation is increasingly deployed not to accelerate timelines, but to reduce human exposure to lethal conditions. China's desert infrastructure projects offer a clear example of this reality. Large-scale solar installations, wind farms, rail corridors, and energy transmission lines are built in environments where survival depends on discipline rather than comfort. Autonomous equipment plays an expanding role, yet even advanced robotics must be adapted to withstand heat, dust, and continuous operation under stress. In these zones, the limiting factor is not technological sophistication, but endurance, both mechanical and human. Every successful project represents a negotiated compromise with an environment that never adapts to human needs. At the opposite extreme, polar and subpolar construction zones present challenges that are equally unforgiving. Temperatures plunge far below freezing, altering material behavior, reducing battery efficiency, thickening lubricants, and increasing the brittleness of steel. Construction windows shrink to weeks, sometimes days, as weather conditions can halt operations without warning. Foundations must account for permafrost that shifts over time, threatening long-term stability even after construction is complete. In these environments, the central question is not how quickly a structure can be built, but whether it can survive decades of thermal cycling without catastrophic failure. These conditions have driven the development of specialized engineering strategies, particularly in northern Eurasia and high-latitude regions. Modular construction allows components to be assembled rapidly during short periods of relative stability. Robotics assists in tasks that would otherwise expose workers to extreme cold, while dense sensor networks monitor structural integrity continuously long after human crews have departed. Survival in these zones depends on redundancy, insulation, and the acceptance that nature, not project timelines, ultimately determines progress. High-altitude construction introduces a different set of constraints, rooted as much in human biology as in engineering. At extreme elevations, oxygen scarcity reduces physical strength, cognitive clarity, and recovery capacity, while machinery loses efficiency and weather conditions change rapidly. Building roads, tunnels, energy systems, and research facilities in mountainous regions requires constant adaptation to both environmental and physiological limits. Workers must acclimatize gradually, rotations are tightly managed, and medical monitoring becomes a standard component of project operations. China's large-scale infrastructure in mountainous terrain illustrates how survival considerations shape engineering decisions. Long tunnels drilled through unstable rock formations demand continuous adjustment, while transport corridors must withstand landslides, seismic activity, and extreme weather. Automation extends human capability rather than replacing it, allowing high-risk tasks to be performed with greater precision and reduced exposure. In these environments, success depends less on raw technological power than on integration, where engineering, medicine, logistics, and environmental science operate as a unified system. What unites all extreme construction zones is the reality that technology alone is never sufficient. Advanced machinery and automation can extend human reach, but they cannot eliminate the fundamental risks imposed by nature. Survival remains the primary variable, shaping work schedules, design choices, and long-term operational strategies. Every project becomes an exercise in risk management, where failure is measured not in delays or cost overruns, but in human lives and irreversible damage. This reality is reshaping how extreme engineering is approached worldwide. Projects are increasingly designed to minimize human exposure rather than maximize speed. Automation is deployed selectively, not as a substitute for human judgment, but as a protective buffer against environmental extremes. Data-driven monitoring allows engineers to anticipate failures before they occur, shifting the focus from reaction to prevention. In these environments, resilience matters more than efficiency, and adaptability matters more than theoretical optimization. Geopolitically, expansion into extreme construction zones reflects a broader competition for strategic advantage. Nations capable of building and sustaining infrastructure in hostile environments gain access to energy routes, resources, and geographic leverage that others cannot easily replicate. Extreme engineering becomes a quiet indicator of national capacity, revealing which countries can operate beyond comfort and which remain constrained by it. From a human perspective, these projects redefine the limits of endurance. Construction workers operate under conditions that demand discipline, training, and psychological resilience alongside technical skill. Survival protocols become routine, medical readiness is constant, and safety margins are narrow. These environments expose the fragility of human systems and reinforce the necessity of designing infrastructure that respects those limits rather than ignoring them. As climate change accelerates environmental volatility, the importance of extreme engineering will only grow. Rising temperatures, shifting weather patterns, and melting ice are transforming previously stable regions into unpredictable construction zones. Infrastructure built today must withstand conditions that did not exist when it was designed, forcing engineers to plan for uncertainty rather than averages. Ultimately, the world's most extreme construction zones reveal a deeper truth about modern civilization. Progress is no longer defined by how easily we build, but by where we choose to build despite the risks. These projects are not monuments to technology alone, they are tests of organizational intelligence, human resilience, and strategic foresight. In deserts, ice fields, and high mountains, engineering becomes an act of survival, and survival becomes the ultimate measure of success. This is the new frontier of extreme engineering, where the question is not whether something can be built, but whether it can be sustained in places where the environment never stops pushing back, and as infrastructure continues to expand into the most hostile zones on Earth, the future of construction will be shaped not just by machines, but by our ability to adapt, endure, and survive where nature sets the terms.